Bismillah Rahman Rahim. In this video, we will discuss two examples related to the DC motors. Our first example is related to the DC series machine that is operating at 800 RPM and drawing a supply current of 50 ampere from a 110 volt DC bus. Armature resistance is 0.5 ohm and the field resistance is 0.1 ohm. We are supposed to determine the speed of the motor if the supply current is reduced to 25 ampere due to the load change. So the load torque is going to decrease, and because of that the armature current is going to reduce to the 25 ampere from 50 ampere. So along with that there is a change in flux as well, that is 45%, and the new flux will be the 45% of the initial flux. So under this situation we need to determine the speed of the motor. So our first step is to draw the equivalent circuit of the machine, and that you can see over here, that is drawn. So this is your field winding, and the resistance of the field winding compared to the shunt machine and the separately excited machine is quite low over here, because the whole of the armature current will have to pass through the field winding as well. So this field winding is connected in series with the armature, that you can see over here in this circuit diagram. So field resistance is 0.1 ohm and the armature resistance is 0.15 ohm, the resistance of this part of the motor. And the back EMF of your machine, that is this one, plus minus AB, that is basically responsible for opposing the current that is being injected from the source. And we are going to apply 110 volt supply to this one. So in order to understand the problem and to do in-depth analysis, the first recommended step is to draw the equivalent circuit of the machine. Okay, then we need to determine the back EMF of the machine when it was operating at the current of, let's suppose, 50 ampere. So what we will have to do, we will have to write down the voltage equation for this one, and the applied voltage is Vt. The voltage drop over here is IaRF. The voltage drop across the armature is IaRa, and then this back EMF. The sum of all of these voltages, the field resistance voltage drop, armature resistance voltage drop, and the back EMF must be equal to your terminal voltage that you are going to apply. So Vt will be equal to IaRa, IaRF, and the back EMF, right? So we can write down this equation like this. And now we want to determine that what is the back EMF at the load when the armature current is 50 ampere, right? So we are just going to plug in the values over here. 110 volt applied voltage, the armature current is 50 ampere, and these are the resistances which are given to us. So back EMF will be 97.5 volt. So at this particular loaded condition, this voltage is 97.5 volt, the back EMF, and the applied voltage is 110 volt. And because of the difference of these two voltages, there is the flow of the current, and that is equal to 50 ampere in this particular case. Okay, now when we are going to reduce the load, of course the current is going to reduce, and because of that what is basically representing that this back EMF has changed. This back EMF is increasing. That's why the current over here, that's the armature current, that will be decreasing, because the current in this depends upon the voltage difference between this point. This is the terminal voltage and the voltage over here is EB. So the difference of these two voltages is basically determining the flow of the current in this branch. So as this current is decreasing, so it means this EB is increasing, because we have kept this one constant. That's why the current is reducing. Okay, so now let's use the same equation that we used over here for the back EMF, and we are determining the back EMF at the new current, and the new current is 25 ampere, that you can see over here. The current is reduced to that one. Terminal voltage is same, 110 volt. Current is reduced to 25 ampere. Armature resistance and the field resistance is same. So the new back EMF is 103.75 volt, right? So you can compare it over here. At 50 ampere, this was the back EMF when the armature current was 50 ampere. Now if your armature current reduces to 25 ampere, so your back EMF reduces. Now the speed change, because the speed depends upon the back EMF, and we have studied in the theory that the ratio of the back EMF, that is equal to the ratio of K phi 1 N1, because your back EMF back EMF is given as K phi into omega, or it can be written as K1 phi into some speed in RPM. This is the speed in radian per second and multiplied with certain constant. So you will be getting this speed in RPM. Overall this is in volts, but I am talking about this unit. This is in radian per second in this, and this is in RPM. So constant will be involved, and you can also represent this one in terms of the field current as well, some constant KB into IF into N. So basically the basic thing that is to be considered over here, that your back EMF is proportional to the flux and the speed. So if you write down the equation for one particular speed, so EB1 is equal to K phi N1, this equation, divided by the second one, that is EB2 K phi 2, because if your flux is changing, speed is changing, you have the new back EMF. The ratio of the two back EMFs can give you the relationship between the speeds. So from here we can write down that N2 over N1, that will be equal to the back EMF 2 divided by the back EMF, means whatever will be the change, in this back EMF, the same change will be appearing in the speed from the condition when your machine was at one particular torque and was taking 50 ampere from the source, and now it is reduced to 25 ampere, the current is reduced. So the back EMF changed, so your speed is going to change according to the same ratio in which the back EMF has changed. Okay, now one thing, and the second thing that is affecting over here is the flux, because when we have changed the load to 25 ampere, so there is a decrease in the flux in the over the poles, and that is now 45% of what it was previously. So what we can say, how we can relate the fluxes, that phi 2 is equal to 0.45 times phi 1, the new flux. So now in this equation that we have seen by taking the ratio of the back EMFs, so if we plug this phi 2, so this is, let's suppose this is 1 phi 1 and this is 0.4 phi 1, so phi 1 will be cancelled out, and the back EMF over here and the back EMF over here of the high torque. So we know about the machine that was running at the 800 RPM. So the new speed will be 1892 RPM from this equation. So it is going to change according to the change of the flux and according to the change in the load, because when the load will be changing, the back EMF will be changing. So the change in speed is basically dependent on the back EMF and the flux. So we already know from the basic discussion of the speed control that the speed of the machine is inversely proportional to the field current. So and you can say it is inversely proportional to basically the flux. So as the flux is reduced, the speed is expected to be increased over here, and that you can observe from this analysis. So what is the key point over here? The key equation is this one, that you are going to compare the back EMF in two states. Back EMF at the one state, that is K phi 1 into N1, and then the back EMF at the second state, that is EB2 K phi 2 into N2. So by taking the ratio, you are going to observe that if the speed is going to change, the back EMF will change in proportion to the ratio of the speed, or if the back EMF is going to change, the speed is going to change accordingly, right? So if the flux is constant, then this can be written as that EB1 over EB2 is simply equal to N1 over N2. If you have the condition when there is no change of the flux, then this equation will be valid, and if there is a change in flux, so then you can use this equation to evaluate the new states. So you can say the back EMF and the speed or the flux at the given conditions. Our second example is related to the DC shunt motors. A DC shunt motor is running at 700 RPM and is drawing 2 ampere at no load from a 110 volt supply. Armature resistance is 0.6 ohm, RF is 100 ohm, and if the input power is 4 kilowatt at full load, determine the speed at full load, torque, efficiency at full load, and neglect iron and rotational losses in these calculations. Okay, so first of all, the equivalent circuit is shown over here. The field winding over here, that is, you can say F1 and F2, and the armature winding A1, A2, that is shown over here, and the resistance, armature resistance is 0.6, and the field resistance is 100 ohm. Okay, so it's a shunt machine, so both the windings are connected in parallel, and here you have the supply connected 110 volt. So the machine is running at 700 rpm. So that can be shown over here, that this machine is running with a certain speed omega in radian per second, and in terms of rpm we will represent it with n. Induced torque is in this direction, and the load torque is in the opposite direction, the load torque. Okay, so at the moment it is at no load condition. So let's calculate first of all the field current, because the voltage that you are going to apply over here, that will be available directly to this winding as well. So the current in this one, if, will be simply equal to Vt by Rf. We will not consider this inductance because this has the 0 volt across it in this steady state. So If is equal to Vt over Rf. So field current is 1.1 ampere by taking the values which are given in the example. Okay, so now what will be this supply current? Supply current will be equal to the armature current at no load plus the field current. So the supply current is known to us, that machine is going to take 2 ampere, right? So this is 2 ampere, and we know about the field current, that is the current in this branch. So supply current is known. So the taking the difference of these two will give us the current in this armature at no load. So armature current at no load will be supply current minus the field current. So 2 minus 1.1.9 ampere is the current that is going to flow in your machine at the no load state, right? And next step is to determine this back EMF at the no load. No load armature current is 0.9 ampere. So writing down the equation for this branch, that this is equal to Vt, that is equal to back EMF plus Ia Ra. So from here, if you rearrange it for the back EMF, that will be equal to Vt minus Ia Ra. So as you are looking for the no load state, so we are going to add a subscript no load. So that will be equal to Vt minus Ia no load into Ra. So 110 volt is the applied voltage, no load armature current, no load resistance. So 109.46 volt is the back EMF at the no load. So at no load this will be like that, and because of the voltage difference over here and over here, certain current is going to flow, and that is equal to 0.9 ampere in this case. Okay, now what we are going to do, we are going to see that if the machine is now going to change, the load on the machine is going to change. So that is shown over here. The input power is 4 kilowatt at the full load. So now we are going to use this one. So the input power is 4 kilowatt. So first of all, we are going to determine what will be the current that will be injected by the machine in your by the supply in your machine. So we know that input power is 4 kilowatt, the voltage is 110 volts, so we can determine the supply current over here at the full load, and that is given by this equation, P in divided by the terminal voltage. So 4 kilowatt divided by 110 volts, so the new source current will be 36.36 ampere. That's the current that is injected over here, and that will be divided into two parts, armature current and the field current. The field current will remain constant because the voltage has not changed. Only the back EMF is going to reduce, so that this armature current is going to increase. Okay, so now what is the current, armature current at the full load? That can be determined from here. Supply current at the full load minus the field current. So 36.36 is the supply current minus the field current, that is 1.1 ampere. So the difference, that is of 35.26 ampere, that is going to flow in this loop. So this armature current is given by this value, right? Okay, now what will be the new back EMF? That we can determine again by writing the motor voltage equation, that back EMF is equal to terminal voltage minus IaRa. So everything is known, armature current, armature resistance, terminal voltage. So new back EMF is 88.84 volt, right? So that you can see, as I explained in the last example as well, the back EMF is going to adjust itself at a new value, so that your machine is going to run the new load and operating at the new speed. So now as no information of the flux is given, and that is being assumed constant because your IF is constant either and the load is changing or not. So because it's a shunt machine is essentially a constant flux machine usually. If there is no change in this circuit, to change the flux over here you will have to connect a variable resistance R if you want to change. Okay, so now comparing the two back EMFs, back EMF in the two states. So back EMF at the full load, back EMF at the full load will be equal to some constant into speed at full load, and the back EMF at the no load will be equal to some constant the speed at no load. So comparing these two, we can write down this equation, and from here we can work out the expression for the full load speed. So that will be equal to the ratio of the speeds into the back EMF at the full load. So if you plug in the values, so the new speed will be 568.13 rpm. So here this machine will be rotating with the speed that is equal to 568.13 rpm, right, and will be giving you certain induced torque to run your load that is applying the torque in the opposite direction. Okay, so initially the machine was at no load. At no load, the speed was 700 rpm. But once you apply the load and your machine is now taking 4 kilowatt at the terminal, so at that time the speed is reduced to 568.13 rpm. Okay, now let's calculate the losses because we are supposed to find out the efficiency. We have determined the speed at full load. This part is complete, and the next is to find out the torque and the efficiency. Okay, so coming towards the losses and to determine the torque, the load torque. So you know that when you are applying this input power, some of the power will be lost across this armature, and the remaining power will be converted into the mechanical form over here, and that will be equal to EB into IA, as we have discussed in the previous tutorial sessions. So that's the power converted into the mechanical form. So what will be that power? That can be determined either by taking the product of the EB into IB, or you can also determine it by considering the losses over here, IA square into RA, subtracting it from the power that is injected at the terminals. So rest of the power will be available over here. So I'm going to take this method now. So okay, one more thing over here, that the power that you are injecting over here is 4 kilowatts. Some of the power is being lost over here, IA square into RA, and some of the power is being lost in this resistance, that is IF square into RF. So that is the power in the form of the heat. These are the copper losses because these are the copper winding. So input power minus the copper losses, the rest of the power will be converted into the mechanical form over here, right? So P in minus the armature copper losses minus the field copper losses. So you will get the power that is converted into the mechanical form, and we are going to call it the electromagnetic power. And assuming that there is no mechanical loss, the shaft power, the power available at the shaft, that will be equal to electromagnetic power over here in this particular case. Okay, so input power, and then these are the losses in the armature winding, and these are the losses in the field winding. So this is the power which is available, 3133 watt, that will be converted into the mechanical form over here, right? Okay, now you can look at the torque. Torque is defined as the ratio of the power and the speed, because you know that the mechanical power is T into omega. So the torque can be determined, that is equal to P over omega. So that you have determined the power available at the shaft. Speed at the full load was this one, 568.13, but it is in RPM, and over here it should be in radian per second. So you are going to multiply it with 2 pi by 60 so that it is converted into radian per second. This is converted into radian per second. So the torque will be 52.66 Newton meter. So this is the torque that will be developed at the shaft because of the power that is converted from the electrical to the mechanical form. So that is the torque induced, and we are going to consider as the T shaft at the moment because there is no loss. If there will be frictional loss, windage loss, so you will have to look at the loss in the torque because of those frictions, and then the rest of the torque will be available to the load. So if that information is given, you can work out the load torque. Okay, so now the efficiency, the power, output power, that is the shaft power that is delivered to your load, that is 3133.03, and the power that you are injecting from here is 4000 watt. So the ratio of these two, the shaft power and the input power, will give you the efficiency 78.3. So it means the power that you've injected over here 4000 watt, this and the efficiency is what we calculated over here, that was 7.83%, 78.3%. So according to that, the power that is converted into the load is nearly 3100 watt. So 900 watt is basically, you can say, is lost in the armature and in the field winding, and of course it will be in the form of the heat. So that's all from this video. Basically we have discussed two examples. One is related to the DC machine, series machine, and one is related to the shunt machine. Thank you very much.